Just a few weeks back, scientists anticipated that 3I/Atlas, the third confirmed interstellar object to visit our system, would glide silently by Mars. But then the unthinkable occurred. Over a mere 48 hours, this cosmic intruder surged dramatically, shining 6 times more intensely than any comet simulation had forecasted, while forming a vast, green-tinged cloud of carbon dioxide roughly half the sun's width. Today, observatories on Earth stand powerless as Atlas hurtles toward Mars at close to 70 kilometers per second, fading from sight amid the overwhelming solar brightness. What makes this apparent extraterrestrial wanderer defy all known norms? Does it hint at groundbreaking physics, or conceal something even more bizarre? What's the mystery brewing close to Mars? And will anyone here on our planet unravel it before it's too late? Right now, 3I/Atlas is positioned about 2 astronomical units from the Sun, double the Earth-Sun separation, or around 300 million kilometers distant. It's plunging closer at an astonishing 58 kilometers per second. That pace is hard to fathom. It exceeds twice the orbital speed of the quickest planet in our system. Even Mercury, the swiftest, circles at under 48 kilometers per second. 3I/Atlas could span the Earth-Moon distance in just over an hour, compared to the 3 days it took Apollo crews. As it nears perihelion late in October, its velocity will surge further to almost 68 kilometers per second, a limit that strains what's possible for natural bodies in the inner solar system. By contrast, the Parker Solar Probe, humanity's speediest craft, will hit about 200 kilometers per second only after multiple gravity slingshots and meticulous design. Yet 3I/Atlas attains this without effort, simply accelerating under the sun's pull along a hyperbolic trajectory. On the astronomical magnitude scale, 3I/Atlas now registers at magnitude 12. Though a technical figure, it holds tangible implications. The dimmest stars detectable without aid top out near magnitude 6. Each magnitude step signals a major shift. 5 steps equate to a 100-fold brightness variation. The shift from magnitude 16 to 12 for 3I/Atlas translates to roughly 40 times brighter. Still, at this brightness, the comet evades naked eye detection. It requires a moderate telescope under pristine, dark conditions for hobbyists to spot it, a faint blur, scarcely set apart from the starry backdrop. This illumination isn't merely optical. It stems from the vast sunlight diffused by the comet's swelling coma. The core nucleus of 3I/Atlas stays concealed, enveloped in a dense veil of vapor and particles. Size guesses vary from a tight 0.3 kilometers to a heftier 5.6 kilometers in diameter. The coma, that luminous sheath encasing the nucleus, has ballooned to nearly the sun's full breadth. Far from an illusion, this is a tangible formation spanning hundreds of thousands of kilometers, composed of solar-heated ices and grains. It scatters and redirects sunlight on an unprecedented scale so far from the sun, setting 3I/Atlas apart from typical comets. Orbital models verify 3I/Atlas's hyperbolic route. It's not gravitationally tied to the sun. This marks a solitary trek through our cosmic neighborhood, with no encore. Its nearest pass by Earth stays at least 1.8 astronomical units away, ruling out any collision or fragment hazards. The pressure comes from the brief chance to study such a rare interloper as it speeds through, soon lost to solar interference. Every measure, separation, pace, luminosity, casts 3I/Atlas as an anomaly beyond standard solar system behaviors. These figures defy straightforward parallels. With a Mars encounter looming, they ground the narrative in solid, irrefutable evidence. Soon after the luminosity surge, the Comet Observation Database, COBS, buzzed with notifications. Stargazers in Australia shared the initial alerts, reporting a 6-fold light boost across 2 evenings. Was this a genuine flare-up, or perhaps light distortion from photometry on October 3rd? As 3I/Atlas streaks by Mars at roughly 30 million kilometers, that's near an astronomical scale, but safely clear of threats to the planet or its satellites. The path drives steadily outward, with an eccentricity over 1, a key indicator of its unbound status. This interstellar guest is on a one-way solar system tour, destined to fade into the void. Earth's minimal approach has passed, holding steady above 1.8 astronomical units, or over 270 million kilometers, almost double our solar distance. No fragments, no strikes, no showers of meteors. The real prize is the observations we snag before the chance slips away. Yet that opportunity narrows quickly. As 3I/Atlas charges inward, the orbital alignment thwarts Earthbound viewers. The separation angle between the comet and the Sun, called solar elongation. The solar elongation of Comet 3I/Atlas diminishes steadily each day. Come October 21st, it drops under 30 degrees, marking a vital limit. At that point, even top-tier telescopes face challenges distinguishing the comet's dim light amid the intense radiance of the twilight heavens. For typical skywatchers, the effective observation period ends in the first part of October, right when the comet draws nearest to Mars. The schedule allows no leeway. Perihelion occurs on October 29th or 30th, as 3I/Atlas swings to within 1.36 to 1.4 astronomical units from the Sun. During this phase, its velocity surges to around 68 kilometers per second, and its outbursts are projected to hit their height. However, from our planet's viewpoint, the comet vanishes into the Sun's brilliance, undetectable by the biggest ground-based instruments. This observational gap, stretching from the start of October into early November, ensures that the comet's most intense developmental stage will play out unseen by direct earthly observation. Such details emerge from orbital simulations, which meticulously chart the comet's route based on countless measurement points. The calculations leave no room for doubt. 3I/Atlas is a one-time visitor. Its hyperbolic orbit confirms that any enigmas unresolved in the next few weeks will linger unsolved for centuries. The pressure stems from opportunity, not peril. It's a fleeting shot to observe an interstellar wanderer as it tangles with our star and worlds before departing eternally. To prolong this glimpse, the relay must shift to probes already orbiting Mars, each equipped with distinct sensors primed to snag fragments of this ephemeral event. The push for information kicked off instantly when 3I/Atlas strayed from its forecasted course. Telescope coordinators worldwide launched a frantic effort against the clock and solar interference. As the comet's brightness curve spiked dramatically, key sites triggered opportunistic observation modes. The Hubble Space Telescope, perpetually in high demand, allocated an urgent slot for imaging, snapping ultraviolet and visible light shots while the coma expanded rapidly. Hubble's team weighed overload risks against resolution needs, tweaking settings in real time to match the object's swift intensification. Shortly after, the James Webb Space Telescope claimed a hard-won, panel-sanctioned interval for mid-infrared analysis. On August 6th, JWST's NIRSpec tool focused on the coma, detecting an elevated carbon dioxide to water proportion of about 7.6, well beyond typical levels for comets in our solar system. This discovery pinged alerts to the Minor Planet Center and sparked buzz in secure messaging groups, triggering demands for more wavelength scans. Next up, the Gemini South facility in Chile shifted gears, securing a series of optical and near-infrared images. Gemini's expansive view and quick adaptability enabled researchers to track nuanced shifts in the coma's form and hue, despite nightly variations in luminosity. At the same time, SphereX, NASA's infrared sky mapping mission, tweaked its survey rhythm to grab fleeting spectral views of the comet. Although not built for swift tracking, SphereX's wide spectral range offered invaluable reference points for monitoring gas releases as the comet traversed varying solar proximities. Every outpost contributed unique capabilities alongside inherent limitations. Hubble excelled at detailing coma intricacies but operated in constrained bursts. JWST provided superior infrared detection, yet its agenda clashed with competing urgent projects. Gemini's terrestrial position suffered from atmospheric conditions and the comet's waning solar separation. Orchestrating these resources demanded precision akin to asteroid defense drills rather than standard comet studies. Facility leaders balanced pleas from rival research groups as processing systems churned through data around the clock to release unprocessed images. Online discussions buzzed with arguments on bandpass selections and durations, since each session carried immense weight. The impending solar conjunction heightened the stakes. Once the comet entered the glare, terrestrial scopes would go dark for an extended stretch. The closing observations, Hubble's UV captures, JWST's CO2 profiles, Gemini's chromatic series, would stand as Earth's conclusive documentation. As the transition to Mars-based assets approached, the terrestrial effort evolved into a showcase of international teamwork, extracting maximum insights from a fading spectacle. When solar conjunction blinds Earth's instruments, Mars emerges as the solar system's premier vantage point. Probes encircling the crimson world abruptly inherit the duty of monitoring an unanticipated comet intruder. Every mission carries tailored instrumentation, prompting engineers and researchers to hastily reconfigure gear and vie for scarce viewing times. HiRISE, the High-Resolution Imaging System. The High-Resolution Imaging Science Experiment, or HiRISE, aboard NASA's Mars Reconnaissance Orbiter stands out for its capacity to detect items as tiny as a desktop from space. Offering a resolution of 0.3 meters per pixel, it could potentially identify the core of 3I/Atlas under ideal conditions, provided the surrounding brightness and alignment for observation align favorably. However, pursuing a comet traveling at 58 kilometers per second from distances of millions of kilometers challenges the capabilities of both equipment and algorithms to the extreme. Specialists from the University of Arizona and JPL conduct model runs, adjust shutter durations, and compete for optimal viewing opportunities. Beyond the danger of overlooking the comet entirely, there's the threat of saturating the sensor or harming individual pixels should sunlight inadvertently enter the frame. Europe's Mars Express, which has been circling the planet since 2003, features the high-resolution stereo camera, known as HRSC. This instrument shines in broad-area, multi-perspective photography, making it perfect for documenting the entire expanse of a comet's hazy envelope and trailing stream. Its spectral filters distinguish particulate matter from vapor, and paired stereo images might uncover faint depth variations within the growing nebula. Operators of the HRSC in Germany collaborate with Earthbound observers to schedule shots precisely when 3I/Atlas nears Mars's path around the Sun. The Trace Gas Orbiter, or TGO, under the ExoMars program, equips the color and stereo surface imaging system, called CASIS, alongside NOMAD, an array of analyzers tailored to spot subtle gases in the atmosphere. Though CASIS focuses on Martian terrain, it can be redirected to photograph the comet's haze across various wavelengths. Its quick capture mode enables monitoring shifts in luminosity and form over a brief encounter. NOMAD specializes in tracing elements such as CO2, H2O, and uncommon organic compounds. Directing its sensors toward 3I/Atlas, scientists aim to verify the heightened CO2 concentrations initially noted by JWST and hunt for molecular traces unprecedented among comets in our solar system. NASA's MAVEN probe contributes a unique vantage, employing its ultraviolet spectrograph to capture signals from oxygen and carbon atoms, as its plasma detectors assess the solar wind's influence on the comet's ejected material. Insights from MAVEN might clarify if the haze's emerald radiance stems from oxygen atoms or rarer mechanisms. Positioned to probe Mars's upper layers, its trajectory offers excellent positions to observe the comet's transit from diverse viewpoints. Control hubs across the United States and Europe hold urgent sessions, balancing the hazards of reallocating tools from standard planetary research. Securing each data-gathering period involves discussions between technicians, lead researchers, and oversight teams. Protective measures remain rigorous. Optics must steer clear of straight solar rays. Analyzers require precise tuning, and assessments of particle risks get thorough reviews. Occasionally, updates to the code get deployed right before action to activate fresh pursuit functions or bypass standard safeguards. None of these spacecraft alone can document the complete narrative of 3I/Atlas. Collectively, this global fleet creates a virtual telescope, merging visual captures, spectral analysis, and particle readings from varied paths and regions. Creativity emerges not only from the technology, but from the swift teamwork among groups that, not long ago, were unfamiliar with this celestial wanderer. With perspectives from our planet dimming, the duty of unraveling an intruder from another star system shifts to these automated sentinels around Mars. Every unit stands ready to collect insights that might transform our grasp of comets and the compositions of bodies originating outside our solar realm. The hues within a comet's hazy sphere serve as a biochemical marker, forged by solar radiation and the evaporating frost from its heart. During September, 3I/Atlas astonished observers when its haze evolved from a subdued crimson to a striking emerald. This change indicated that an atypical event was unfolding inside its broadening sheath. The haze's immense scale proved astonishing, extending almost halfway across the sun's width, exceeding 600,000 kilometers in breadth. Far from an optical deception or lighting artifact, the emerald radiance proved genuine, calling for a clear rationale. Conventionally, verdant comets derive their tint from C2 molecules, which glow in the Swan bands around 510 nanometers upon solar excitation. Nevertheless, as experts examined records from Gemini, VLT, and JWST, the anticipated C2 spectral peaks were absent, without Swan bands or signs of the typical carbon pattern, despite the haze's growing intensity. Rather, the observations suggested an alternative source. JWST's observations from August uncovered a CO2 to H2O proportion of roughly 7:6, a remarkable figure well above the norm for solar system comets, where ice usually prevails. This discovery redirected focus to oxygen atoms in particular, especially the prohibited OI line at 5,577 angstroms. This emerald feature emerges when solar rays and high-energy particles dissociate CO2 and H2O, releasing oxygen that releases green light while returning from an unstable configuration. Within the thick, CO2-laden haze of 3I/Atlas, ultraviolet sunlight and photoelectrons function as accelerators, converting the area into a producer of emerald OI output. Benchtop tests and earlier comet investigations back this mechanism. However, 2I/Borisov elevates this process to unprecedented levels. Even at a distance of 2 astronomical units from the Sun, the environment favors this phenomenon overwhelmingly, surpassing the scattered dust continuum and generating the haunting emerald radiance that now characterizes the comet's visage. Other theories were explored. Scientists hunted for CO fluorescence, dust scattering, and unusual plasma phenomena. Yet the scarcity of CO and the stable dust profile rendered these improbable. The discussion progressed live as experts exchanged unprocessed spectra and calibration codes, scrutinizing each fresh data set for signs of C2 or additional carbon molecules. Ultimately, agreement coalesced around atomic oxygen as the primary source. The sequence of events was persuasive. The verdant phase emerged precisely when CO2 emissions spiked and as the comet entered the zone where solar ultraviolet radiation could effectively dissociate molecules within the broadening coma. Dr. Lena Sato, principal spectroscopist for the JWST group, likened the effort to pursuing an elusive quarry with an ever-altering demeanor. Every spectrum documented a dynamic regime where chemical reactions and physical forces intersected on a grand, seldom observed scale. The missing C2 signal represented not a setback, but an indicator that 2I/Borisov functioned according to principles alien to comets native to our solar system. That emerald luminescence emerged as its hallmark, emblematic of interstellar reactions and primordial ices forged in a distant stellar cradle. The enigma persists. With the coma continuing to develop and Mars spacecraft gearing up for fresh scans, the quest for conclusive spectral signatures, whether C2 or an otter variant, presses on. Each observation might clarify if 2I/Borisov is merely a comet strained to its boundaries or a harbinger bearing enigmas from outside our stellar domain. The following inquiry concerns how this reactivity influences the comet's form. And what insights could the counter-narrative offer regarding the dynamics molding this extraterrestrial interloper? A solar-directed streak pierces the coma of 2I/Borisov, defying the conventional depiction of a comet's tail. Rather than streaming sunward, this countertail aims directly at the sun, detectable in Hubble photographs and terrestrial observatories alike. The standard account, a visual illusion during Earth's passage through the comet's orbital plane, fails to apply. The alignment is mismatched, and the countertail's endurance across weeks suggests an underlying mechanism. Specialists in plasma dynamics and orbital behavior have zeroed in on the underlying processes. 2I/Borisov is chiefly powered by carbon dioxide rather than water, with its emissions exhibiting stark irregularity. Solar illumination strikes the nucleus obliquely, propelling streams of gas and dust predominantly from the illuminated hemisphere. Such asymmetric outbursts propel substantial dust particles outward, though not symmetrically across all vectors. The most vigorous ejections arise where insolation peaks, extending a vaporization boundary deeper toward the sun than in ordinary comets. Particles ejected along this trajectory are larger and less swift, capable of withstanding radiation pressure and thermal stress for extended periods. Consequently, a tangible countertail forms, an arch of hefty grains that endures for tens of thousands of kilometers prior to eventual vaporization. Simulations suggest these particles measure at least 10 microns in diameter, massive enough to defy the solar wind and maintain their solar approach. Their longevity hinges on both dimensions and composition. Whereas CO2 ice dissipates rapidly, particles incorporating darker, more refractory substances can persist sufficiently to form the noted structure. The countertail's intensity diminishes sharply along its length, aligning with projections for grains progressively eroded by solar flux rather than merely redistributed in vacuum. Magnetic interactions introduce further intricacies. As the coma enlarges, it serves as a laboratory for plasma exchanges. Electrified dust particles engage with the solar wind and the comet's emissions, yielding focused currents and protrusions that may warp the countertail. Nevertheless, for 2I/Borisov, the core solar-directed element stems from particle durability and directional jets, bypassing esoteric plasma behaviors. The ion tail, molded by the interplanetary magnetic field, extends anti-sunward predictably, distinctly detached from the countertail's route. Speculation has ventured into artificial origins, constructed forms, emergent plasma assemblies, or even extraterrestrial artifacts, but observations refute such notions. All observed traits conform to established cometary principles, albeit tested rigorously by the object's singular composition and vigor. Dr. Rafael Ortiz, plasma expert from the Mars Orbiter Initiative, encapsulates it neatly. To validate the remarkable, one must first exclude the commonplace. To date, the countertail exemplifies routine physics. The ultimate validation awaits. As 2I/Borisov negotiates its solar closest approach and Mars probes compile records, projections of particle dimensions, jet directionality, and plasma linkages will undergo rigorous scrutiny. Should the countertail dissipate or break apart as anticipated for CO2-propelled grains, the argument for innate origins solidifies. Otherwise, novel principles might emerge. Beyond perihelion, 2I/Borisov ventures into its most erratic stage. The MOD scientists are divided into factions, each harboring distinct predictions for the comet's future trajectory. Certain experts anticipate a gradual dimming, with luminosity waning as the volatile ices deplete and the surrounding envelope contracts, ultimately yielding a dim leftover that meanders into the distance. In contrast, some caution about an explosive finale, a burst of intensified glow ignited by untapped reserves of carbon dioxide, or an abrupt crumbling of the core, mirroring the demise of comets that have shattered beneath the sun's relentless pull. Another option figures prominently in the assessments of orbital specialists: total breakdown. Should the core prove as riddled with voids and cracks as its erratic outbursts imply, the closest solar approach might trigger its dissolution, hurling debris that temporarily boosts the brightness profile prior to dispersing into obscurity. Dr. Mara Valente, a specialist in comet orbits monitoring the phenomenon, portrays the upcoming period as a rigorous trial for all hypotheses concerning rogue bodies from interstellar space. Her team's computational models outline numerous possibilities, each linked to particular indicators. A steady decrease in luminosity suggests straightforward vapor release. Unpredictable surges or sharp plunges may indicate splintering. A lingering greenish envelope post-closest approach would indicate substantial hidden layers of carbon dioxide-laden frost, whereas a quick return to reddish or bluish hues could expose the depletion of those reactive strata. The implications extend far past the destiny of one celestial body. 32/Atlas serves as a messenger from a remote stellar realm, bearing the chemical makeup and architecture shaped in some far-off cradle. Its actions challenge the boundaries of cometary science, probing how embedded frosts endure voyages across the void, the ways particles and vapors engage with solar particles, and the accuracy of our frameworks in forecasting the existences of entities that linger for eons amid the stars. Whether it dims quietly, blazes briefly, or shatters apart, each result supplies vital insights to bolster defenses against cosmic intruders, sharpening our methods for detecting and analyzing future interlopers that could eventually present genuine hazards. Outlandish notions, ranging from artificial artifacts to biological energy forms, hover at the periphery. Thus far, no data backs these notions, yet the rigorous process of inquiry requires caution. All irregularities deserve scrutiny through commonplace mechanisms prior to resorting to the improbable. The close pass by Mars and the solar proximity phase offer an uncommon testing ground, where theoretical forecasts can be evaluated against actual occurrences and the divide between established knowledge and potential novelties is probed live. Critical dates are already highlighted. Data from Mars satellites emerging in early October, solar nearest point on October 29th and 30th, and resumed observations from Earth in November. The coming period will determine which frameworks endure and which demand revision. At present, the narrative of 32/Atlas unfolds as an ongoing trial racing through the cosmos. Through each fresh sighting, an opportunity arises to peer into the mechanics governing realms outside our solar neighborhood. Despite cutting-edge tools, certain stellar guests depart with enigmas outweighing resolutions.